Hi. As I said, I'm Ana Jed, and uh, I'll be talking with you today about what the Mars 2020 Perseverance rover is doing in its search for life and why, when looking for life on other planets, it's important to have a good understanding of that planet's geologic history. So what we'll be covering is looking for chemical elements in the planet's soil, the kinds of rocks and erosion in the area, and the magnetic history of the rocks present on the planet. I'll be talking with you about this because I believe space and Mars are amazing, and this is the first, and this is the first time that we'll be going up, being able to bring back Martian rock samples to Earth, and I think that's very cool. And also because I think being able to use chemistry and geology to paint a better picture of what's happened to life on other planets like a million years ago is really fascinating. I'm sorry, I think I've lost. Oh, there we are. Okay, so looking at the chemicals in the soil, in 2011, this image of the Jezreel Crater, which was once thought to have been a crater lake, was captured by the Mars Reconnaissance Orbiter, and analysis by instruments on board the orbiter showed the presence of clays and carbonates in the Martian soil, which are two items whose presence on Earth are indicators of often water and possible life. This because carbonate functional groups form naturally when carbon dioxide comes in contact with water and combines with other elements such as calcium to make carbonate molecules, which are used by lots of marine organisms to build their shells, and thus being water and life being present in that area. It was this examination of chemicals in the soil of Mars, along with other similar finds elsewhere on the planet, that brought this sort of hope for finding more signs of Martian water and microorganisms by taking a closer look at the soil. It's also why ultimately the Jezreel Crater Delta Formation was chosen for closer examination by the Mars 2020 rover mission. So now, looking at the types of rocks they found and their conditions, once the rover was actually on Mars, the scientists thought that they would be finding sedimentary rocks in the crater, due to that being the most common form that carbonate rocks take on Earth, as well as pictures that had previously been taken that seemed to show the sort of distinct layering in the rocks, which is a common feature for sedimentary structures. However, once they got there, much to everybody's surprise, it was found that the ground around the delta was instead made of igneous rock. The stratification or layering was determined to have come from differences in the mineral crystals formed during the lava's cooling. Recently, one of these minerals, olivine, has been discovered or is being discussed as being a mineral essential to the emergence of life. So its presence here is also a positive indicator of the area once having been able to support life as well. The types of minerals we see and where we see them are all clues to understanding Mars's formation and the possible life that could have lived there. And so we need to understand the planet itself and how it was put together to understand how life once could have been supported. Another amazing thing to keep in mind is that igneous rocks can also be dated by measuring the elemental radioactive decay. This can give us a better picture of the timeline of the geologic history, which in turn can help us date any signs of life that we do find and help us figure out what may have actually happened to it. Also, as far as erosion goes in this sort of area, these igneous rocks were found to have signs of salt weathering in them, with holes and divots in their surface lined with salt residue, similar to those found on Earth. This is both a sign of water's past presence in this area, as well as it being an area high in mineral content and likely friendly to life as well. And the last thing I want to talk to you about is that another aspect of what the rover is attempting to record while up there is changes in the strength of Mars's magnetic field to see if it once might have been able to have a better chance of holding a thicker, more life-supporting atmosphere to Mars's surface. With paleomagnetism, we can use rocks to determine the magnetism induced by the planet's magnetic field at the time of that rock's formation by looking at the orientation of iron in the rock, and therefore the strength of the planet's magnetic field at that time. Mars currently has no planetary magnetic field, only patches formed from magnetic mineral deposits in the crust. Indications of changes in the magnetic field, along with dating the rocks, can help us narrow down when Mars may have lost its atmosphere altogether, which is, important to understand for life. So knowing this and the planet's history can also help us paint a clear picture of when or what actually may have eventually happened to any of evidence of life on Mars that we do find. So being able to understand a soil's chemical makeup and the kinds of rocks present and the dates of different geologic layers, as well as their conditions and the magnetic history of the area, are all things that can be understood geologically about a planet and provide us with context about an area's conditions and its life-supporting capabilities before we ever actually find a fossil or preserved organism. And geology can be important to understanding all parts of the planet history, and I think that's something very important to understand. Thank you for listening.